Hi, this is Frank again from GeoComposites. The purpose of this part of the presentation is to introduce you to the software that we use to interface and control all of our printers. The name of the software is something called Eiger. It runs in a simple browser. Eiger allows us to be able to control any kind of printer or any kind of 3D printing additive asset that we have on the network. So in our case, it's going to be a metal printer, it's going to be a carbon fiber composite printer. On the carbon fiber composite printers, this will control the industrial printers as well as the desktop printers. And the way that it works is quite simply, I open up an STL file. So this is the impeller that was created for us in CAD. In CAD, we said File, Save as STL. In Eiger, we said File, Open STL, and it brings it into our view like this. The grid on the bottom represents the print bed. And then I select the material that I want to print it out of, and if I want any reinforcement material, any carbon fiber or continuous fiber reinforcement material. So for this example, I'm going to say, no, I'll just print it out of the base carbon fiber material, Onyx. And this is what the internal view looks like. So if I had the ability to do an X-ray view of the part, this is exactly the way that it would look, and allows me to see the architecture of the part, the infill. I can view the part layer by layer, so I can actually see by hitting the right mouse or right cursor button on the keyboard. I can see layer by layer. Here's exactly what the toolpaths look like, including the infill. I can go back to my 3D view. Now, let's say that I want to add some continuous support to the part. So I'll view this version of the part where we did add some continuous carbon fiber reinforcement. And under the reinforcement settings, we said, well, we'd like to have 50 layers of continuous fiber, and we'd like that laid up concentrically. So if I look at the internal view, it'll allow me to see, here's the way that we've got the part or the continuous fiber laid out inside of the part. So in this example, I did it concentrically, and I also did it isotropically. So across this base, you can see the isotropic pattern, and you can see concentric around the outer walls and the inner walls. So I can control exactly where the continuous fiber reinforcement gets placed on the part. And today I'm going to talk to you a little bit about the carbon fiber composite equipment that we have located here. Specifically, we have a Markforged X7 printer. So the Markforged X7 is an industrial strength 3D printer. It really specializes at creating parts that are functionally, dimensionally accurate parts and very, very strong. So the X7 prints a couple of different base materials. One of the primary base materials is this black material. We call it Onyx. Onyx is comprised of chopped carbon fiber, which by definition, just chopped carbon fiber makes it very, very strong and very, very lightweight. In addition, at the same time as we're printing the Onyx material, we can print one of 4 different continuous materials at the same time. So the 4 different continuous materials consist of carbon fiber, of Kevlar, which is what this material is. We can print continuous fiberglass. We also have a continuous high temperature, high strength fiberglass. So what each one of these materials do is that they add additional properties to the already very, very strong and dimensionally accurate part to make them even stronger. By virtue of adding reinforcement material to the part, we can use it potentially as substitutes for a variety of metal applications, where in the past you might have used metal parts, for example, for end-of-arm tooling or work holding applications. Now we can 3D print those. The benefit of 3D printing parts that are used for work holding, in this example, this is a metal part that maybe I'm going to clamp onto for an end-of-arm tooling or for a jig or a fixture. By using the carbon fiber material and clamping onto your metal parts in production, the carbon fiber material is non-marring, so I'm not going to scratch your part. I have a desktop printer. So the desktop printer is really the same as the industrial printer, smaller part size rather. So for smaller parts, again, great for work holding applications. The last step in the process, it is kind of optional. It's a kind of a QA/QC process that we employ here in our lab, is that we utilize 3D scanning to be able to measure the parts. So what we have the ability to do is take the physical part, we can 3D scan the physical part, and then in software we can call up the CAD version of this part. We can overlay the 3D scan of the part, and literally within a minute or two we can tell you if the part physically matches the CAD. So we got out of the sintering oven through the entire printing process exactly what we expected, or if the part is deviating a bit for whatever reason, where is it deviating and how much are we deviating?
Okay, so as I've described before, the part's now in the brown state. Once we verify this, we can then sinter the part. As it was mentioned, it's usually roughly around 24 hours. Our part's complete, and we're now going to remove this from the sinter. With the set of safety steps, we can then remove our sintered part from the machine.